Okay, so we've dug down into some of the physics of PV, how they work, as well as a little bit of the manufacturing. So reducing costs and raising efficiency. So I just mentioned that the process we were looking at, the Tucholsky process, is single crystal silicon, high purity, high temperature, relatively long time. Polycrystal, though, just means that I'm going to freeze this thing quickly. So I've got individual crystals that are there, but there are now so-called grain boundaries but between them. They're not aligned in space perfectly, as it were. So in the polycrystal, yeah, there's your classic, and that's what you see with most PV panels. So every one of those colors represents an individual crystal grain that formed during the formation of the polycrystal. And again, here are your conductors. Each one of those little stripes on top. That's your top conductor that we talked about before. The issue with that, at that, in a pretty good example would be every one of those little intersections is like the cloverleaf on an interstate or a stoplight in town. It's just a little more room for a traffic jam, and a little more room for inefficiency. So that nice clean looping or that wave analogy that we talked about, well, it's a breakwater or something that gums up the traffic of flow of electrons. But the other point, though, in the polycrystal, each one of these grains is still crystal silicon, still in that crystalline form. That's why it's called polycrystalline. All right. Gallium arsenide, that's the one I mentioned previously. That's what these folks are working on in Japan. So here's silicon, here's gallium, and here's arsenic. So gallium is providing the same role that boron did, arsenic the same one as silicon. See you around, Daniel. So basically the same idea. They've got the either the extra electron or the missing electron, as the case may be. Okay. This does say that cells made from gallium arsenide are substantially more expensive because they involve epitaxial crystal growth. So again, you've got the this gas of gallium arsenic coming in to work its way into the crystal lattice, rather than the method we talked about with the phosphorus and the boron. Okay, so these are a few things to keep in mind. The valence band, that's that lower energy state. Those are these lower energy electrons down here, this so-called valence band. The conduction band is the higher energy level, and then the energy gap or the band gap is just the difference between the two. It's the amount of energy that jumped from the valence up into the conduction. So as it's mentioned here, metals have many electrons in the conduction band. Insulators have none. Semiconductors, a little above.
So insulators would just bounce the energy back rather than to make them inert?
Exactly. In the case of an insulator, a photon comes in, it's either going to bounce off, it's going to be transmitted, or it's just going to be absorbed as heat. It's not going to come in as electricity, it's just going to turn into heat. Yeah. Okay, so here's the maximum theoretical efficiency in a single silicon PV is about 30%. And that's just for silicon. Remember I said I was there at Tohoku University and these guys are hitting 48%. It's because they're not using silicon.
What was they using?
Gallium arsenide. Yeah. They might have even been using some germanium. I can't remember 100%, but and there are even even some that'll use some tin, some indium. One of the neatest things too, there's even a metal that's transparent. It's indium tin oxide. So if you ever see ITO, I mean, you could actually use ITO as your conductor on the surface, and you get rid of that reflection altogether. Yeah, Mariah?
So what would be some of the environmental implications of harvesting these types of materials? Like, it seems like silicon maybe more available. I don't know.
Yeah, it's a good question, and I do not know exactly where germanium is mined. I know arsenic is everywhere. Tin is everywhere. Indium not so much. Antimony not so much. I do know that in a lot of mining processes, when you go after something, and a lot of other stuff just kind of comes along for the ride. Is that right? Yeah. Yeah. So I think a lot of times, yeah, you can just kind of think of it as a byproduct, and right, and as I guess from my standpoint, what you don't want to have happen is once you're done making the thing, it just goes off and ends up in a river or somewhere in the environment. In my thinking, okay, we pulled this stuff out of nature, let's do something useful with it, and not just put it back eventually. So,
Or even like the older cells that have gotten worn out, like it seems like they should be able to be recycled.
oh yeah,
some way.
yeah. There's a brand new paper just came out of China on a low-cost, high-efficiency method for recycling
Yeah,
solar.
It seems like we've had over the last 50 years produced tons of electronics, most of
Oh,
which
yeah.
we're not recycling
Yep.
parts from, but should be because it's a major environmental cost to be.
Well, we're doing exactly that. I've got one of my graduates just started her what she calls Oreos refining, and so she is refining precious metals from electronics. It's been a struggle getting a deal going with the university, but between Montana State and the University of Montana, we ship about $500,000 of gold to California every year just in our electronics. So we're working on that.
That's
Yeah.
The
Yeah.
Sustainability Board was just talking about how they're trying to renew their effort to do e-waste recycling on campus.
Yeah.
But I guess there's just a couple of legal things that they have to jump through, so they've been working really hard.
Yeah, and
They
it's.
were doing it for a while, but then it's just something weird happened.
Well, we're still working on it. Yeah, and it's funny when you start digging around, like who's really in charge here?
It seems like that type of thing would be really beneficial because it's essentially free materials other than transportation
Sure.
and the cost of getting it out. Like it must be cheaper to recycle it than to mine it.
Yeah, absolutely.
Recycle it, then refine it.
Yeah,
Then
than to
mine it.
mine it.
Oh, the mine it. Yes and no. Yes and no.
Depending on what it
Yeah,
is.
yes and no. Yeah, that's right. And it's a little bit of a chicken and egg problem because you need to do the recycling or refining takes energy. I mean, pulling these materials that have been stuck together apart does take energy and tech. But no, I am full agreement with you on that one. Another thing worth noting is that there's a new energy unit to keep in mind. It's called the Electron Volt, and there's a conversion between the Electron Volt and the Joule. If memory serves me correctly, I think there are 10 to the 19th electron volts in a Joule. Let's look it up really quick. Electron volts to joules. 10 to the 19th. So an electron volt is essentially the amount of energy to get an electron from here to here. You can kind of think of it that way. I'm going to take a single electron and push it from there to there. Well, how many, if I've got a joule of energy, how many electrons can I push from there to there? 10 to the 19th. What is that? 100 million trillion? Something like that. So it's a kind of a strange number, like, is it a volt? Is it a joule? No, it's an electron volt, and it's energy. It's the amount of energy to push that electron up from the valence into the conduction. And so the photon itself has that much energy. And let's get to the chapter, and I'll show what I mean by that. Okay, pretty cool. Crossed the finish line with more energy than they started with.
How hot is it?
I've built a couple of those. Australia, you're probably talking 90, 100 C. Yeah, it's up there. But with this nice wind, you've got the convection blowing the heat away from the cells. We actually did this a couple of years ago in our practicum. I had my students hook up a couple 12-volt fans, computer fans to the cells, and at a certain temperature they kicked on. The fans themselves were pulling 2 watts, but the panel bopped up by 4 watts. So, the temperature's hot, which diminishes the efficiency of the cells, but if you have that convection, you're sort of constantly cooling them. The buildup of heat. Yeah, air cool. And they said sharp triple junction 3.5 PV cell, 30% efficiency. When we showed up to the Shell Eco Marathon with our car in 2012, we were racing Purdue University. They spent more on their solar panels than we had in our entire budget. So they had a $15,000 solar array that was built by Boeing or Lockheed or whatever, and we showed up with our car. We had actually soldered our own cells together, and they got a flat tire and couldn't figure out how to fix it. But we were able to rebuild our entire car in one night and take it from a 12 volt to a 24 volt system, because the 2 motors that were donated from Jor burned out on it. Oh my gosh, that stunk. But Alaska's like, here, take our hub motor. So we were able just in one night to rewire the whole car and actually race the next day. So this stuff is fun. Not easy, not cheap. I mean, that's a $1 million car right there. I mean, it just is. I mean, that's how many dollars it took to make that car.
Was this model in the picture manned?
A big 60 though.
Yeah, a little 60. What?
Was it manned?
It is manned. There is a human being right there.
Sweating. Oh,
Yeah, sweating. Hungry, sweating, pulling an all-nighter, still driving.
28 hours.
Amorphous silicon. So in this case, you just kind of throw the whole crystal model out the window, but it's better than nothing. It's like, okay, I'll take a gravel road. You don't have to pave it. I'll get there eventually. Think the amorphous like it's the gravel roads, the broken up chunks. And we have a few of those sitting over at the Missoula International School right now, and they're easy to make. You can make it more flexible. Yeah.
Speaking of that, have you heard any new advancements in solar pavement?
A little bit comes and goes. Solar pavement, yeah.
There's that solar roadways movement from last year.
There's some solar roadways movement.
So inexpensive.
Yeah, it's really expensive for like less than a mile stretch in Germany. It's
$1 million a mile actually seems pretty cheap to me, believe it or not. Yeah,
Wow.
$1 million a mile seems.
France is building a highway.
That's the plan. I mean, that's the plan. That's Solar City and Tesla right there combining forces. The whole interstate system. There's a lot of real estate between those 2 lanes. Just solar.
How many, you don't need to pave all of the roads
Sure.
in order to produce enough power.
No.
So it's expensive, but I guess if you think about probably the fractions that you need, it might not.
Well, and it's similar to the first subway, right? Like, why would we spend $1 million digging a hole underground? Let's just jump on your horse, But at the end of the day, it's progress, right? You can sort of.
I'm really glad that Elon Musk is staying on Trump's advisory council too.
Sure.
Oh, I can't even believe that.
He's getting a lot of shit for it, but
Well,
thank God somebody,
yeah.
at least one.
Yeah. No, I listen to Rush. I go and get interviewed on KECI. I don't mind diving into the, because you have to engage. I mean, you really do. You really do. Okay. So there's amorphous. Silicon oxide. Oh, I mentioned ITO, Indian Tin Oxide. So that's actually a transparent conductor. It's a transparent metal. That's what the guy looks like. That's the amorphous. So here's your conductor. So the glass and the silicon dioxide, oxide will stiffen it. Otherwise, these things are just so. I mean, when we were soldering these together for our car, it's like soldering Pringles potato chips. All right. So here's some others, and I mentioned multiple junctions. So let those higher energy photons penetrate deeper into the cells. The Tohoku University guys are actually, instead of having a layer here, they actually have quantum dots. They're actually little balls of semiconductors that act more like, so a quantum dot is like a chunk of matter that acts more like an individual atom than like a chunk of matter. And so they're just more efficient. It's the best I can do.
Tin rolled in, or is iron rolled in some kind of?
These iron, I'll see if I can find the papers, but the iron is sort of a sacrificial material. It was just used initially. So imagine a whole lot of iron, nanoparticles. Each one is maybe 10, 50 nanometers in diameter, and they're dotted on top of it. Then the neutron beams come in and sort of blast out chunks, and what you're left with are little islands, and each little island still touches the junction, but there's no. So the traffic flows in this direction and very little in this direction. That's the idea. It's like, okay, interstate highway, straight from P to N, no cross streets. Okay, concentrating PV. And the idea is, it's tough, it's hard to make these materials, so let's just pop them out like little balls, and just like our Fresnel lens or those lenses we saw with solar thermal, let's just fire all the electrons into that one little goodie basket. And this isn't, these are relatively large. It's 2 to 3 millimeters in diameter, and the ball's a millimeter. So you see them. Yeah. What's pencil lead? When you do your mechanical pencil, I mean, it's
Used to be lead, but they.
yeah. So it's a little. So it's as big as a fat pencil lead, 0.9 millimeters. Here's another one too, where in general, engineers, and a lot of times people joke like, oh, it looks like an engineer designed that thing because it's just kind of boring, square, round, exactly round. But if the surface is more rough, more fractal, less predictable, then the chance of the photon coming in might be a little greater. That's the idea behind this rough surface. And there's even MIT pops up some of their latest and greatest, and what they came up with not too long ago. I'll just do a little.
If it was flat, would it just have a greater chance to deflect?
If it was flat, it would have a greater chance of reflecting. That's exactly right. So MIT came up with this kind of weird, it's almost like a house of cards PV array, and so each cell isn't going to get that much radiation, but combined, the way they're sort of stacked together, even think back to chapter 2, where there were those mirrors sort of reflecting light down in between buildings. Similar thing, they're sort of set up in such a way that they're sort of going a little more 3D, like vertical guarding. You might have heard of vertical guarding. Like, so let's just capture all the photons rather than having some of them bounce off. Okay, emerging and novel. So nanoparticles, nanocrystals. And like I said, I'll go and find that paper from Onagawa University, because that's where we are now with these things. Okay, so once they're put together, I mentioned previously that the cells themselves are relatively low voltage, and we need to get current and voltage out of them. So the current is going to sort of flow through our circuit. That's our load, whatever that might happen to be, lights or motors, etc. So voltage is across the two, the positive and the negative, and current flows through. And when you multiply current times voltage, you get power. Now, this is the sweet spot for operating. So if there are no volts on the system, you can have a lot of current, or if you open it up, you can have a lot of volts building up, but no amps. So anything times zero so this is zero power, this is zero power, but somewhere out here on this so-called knee is the sweet spot. And there are sophisticated circuits on every one of these inverters for sort of doing what's called maximum power point tracking. Because what you're trying to do is maximize the area of that rectangle. If I move the dot over here, it comes down here and I've just got this little tiny chunk at the bottom. If I move the dot over here, I've got this little chunk. But somewhere, out on that knee is the maximum, right? So you can sort of, imagine tuning that like you would a radio so you've got the best signal coming through. There's your volts and amps. Yes?
So you do that by measuring what kind of, how much current you have coming in?
You measure it by taking the product of voltage and current and maximizing it in such a way that it's maximized. It's sophisticated. There's a lot of circuits there, but you could think of it as like, hey, we all want to get out the door. Do I make the door wider, or do I shove a little harder? Right. So, so all right. That's the best analogy I can come up with. All right. We've all seen these parking meters, buoys, antennas. Off-grid, if you're going to go off-grid, you're going to need some storage. And in this case, this just happened to be a Lighting a Billion Lives project, PV-powered lanterns, some batteries. So we're going to see more of this with the power walls. We don't see it yet in Montana, but in California there are 2 and sometimes 3 different rates depending on when you're using electricity. So the utility's like, hey, I'm not going to give it away, but I'll sell it a lot cheaper at midnight than I am at 8 in the morning. So you can imagine setting your own system up in such a way that, hey, I'll buy it now, sell it later. Solar City just did a giant project like this in California because they know the rates are different at different times of day, so they're just pulling this in. And that's large scale, but if you're going to go off grid, you're still going to have your own little microgrid at your house. You're going to need some kind of storage, and so here we go.
And are all of those batteries linked on the same sequence to increase the efficiency? They all charge and drain at the same
Well,
rate?
if I were designing this system, I would say let's charge all of these first, all of these second, and all of those third. Give them all a full charge rather than just, give a certain fraction of full charge rather than giving them all just a wimpy charge. But you can imagine a lot of different scenarios depending on how many people you were trying to serve with this. Right? And that's just, logic circuits. There's a 4 kilowatt system. Most systems in Missoula you'll see are 2.5, maybe 3 kilowatt systems. And that is typically more than enough to zero out your bill and just pay your connection fee.
What's it usually cost Polycrystals to set up?
I'm seeing $4 a watt typically right now in Missoula, so 10 grand. Yeah, 10 grand for 2.5 kW system.
I guess it would take you to pay that off.
Payback in Montana is somewhere on the order of 10 years.
So you have to know that you're going to be living here.
Well, or not necessarily. By putting the PV on the house, you've increased the value of the house. So all of a sudden, someone says, "Oh, I'm going to buy that house now. I'll pay you a little extra because I know I'm not going to have to pay the utility bill down the road."
So then you can pay it off with whatever.
You put the investment.
$200 a month you're saving on every
That
month.
probably did,
Yeah.
sort of that depend though on
Well,
how
maybe
much
not that
you
much.
sold the house and like how cheap it is to put.
It would. It depends on a lot of things, absolutely.
But it
Yep.
costs you about the same every month as a regular utility bill to pay off the solar, right?
Yep. And so Solar City has actually come up with some financing packages where they don't charge anything up front.
Mhm.
You just pay over time like you would a utility bill.
Yeah.
So to the consumer,
Yeah,
It
is that
does make a
Great.
difference.
sort of like the situation where some companies will like just still own the solar panels? and
Could be.
they're just paying you for real estate basically?
Yep, sort of like mineral rights. Yeah, you might have your solar rights. Yeah.
That seems like a bad idea.
Well, yeah.
Seems like.
Yeah.
But, so if someone installed a solar panel on your house and you decide you want to move, but you're still staying in the area, could you technically, you could have them come and take it off and install it on a different house?
I guess you could. Yeah.
I'm just curious.
I guess you could. I
What are
don't.
solar
That seems a
companies
little.
willing to do?
Yeah, it seems a little weird to take your panels with you, but. There's also community solar, and there's a few examples now where I don't want them on my house, but I'll pay over here and I'll have that as part of my energy.
Just having space in the yard,
Yeah.
set aside.
Yeah. And again, here we're seeing the progress in what's called grid parity, where it's actually cheaper over time. The levelized cost of solar actually does become cheaper. And it depends, like how long you want to wait to get your money back, but yeah, there it is.
And not to mention the other factor of, how the main source of energy is generated.
Yeah.
Reduce the emissions.
Yeah. Here's the key though. See those modules? They've been the key driver in bringing the cost down. Labor doesn't change that much, but cost of capital, has its own costs associated with it. But it's really those modules that have been driving the reduction. And then you asked Mariah about environmental, and there's a few things out there about where these things come from. So anyway, that is chapter 3, solar-powered aircraft. Yeah, so good luck on the exam. I think I'll give you a couple shots at it.
Do you have a certain amount of time, like if you start it today, do you have a certain amount of time to complete
I
it?
think it's a 3-hour time limit.
Okay.
And
Yeah.
the
So you
timer
can't
keeps
just like
going.
take the whole weekend?
I don't think so.
Yeah,
I
once
think
But you get
start,
two
I think it'd be-
chances, though.
I think it'd be safer just to dive in and have a look at every problem. Take a shot at it, and then
And then do it.
yeah.
But not-
Yeah, I always take notes on the things that I get wrong and go and look them up
Yeah.
again and just,
Yeah. Yeah.
You can always save the results